In this lesson, we will look at how to determine whether two straight lines are parallel, skew, or whether they intersect. And in the case where they intersect, we will look at how to find the point of intersection. We're first going to consider these two lines in two dimensions. We've got R1 equals minus 4, 2 plus lambda 1, 1, and R2 is 1, 4 plus mu 2 minus 1. So we're going to look at what these lines look like when plotted on a graph. So if we start with the origin, the first line, the position of the particular point is minus 4, 2, and then the direction of the line is 1, 1. So the first line is as shown. And then for the second line, the particular point on the line is 1, 4, and then the direction of the line is 2, minus 1. So we can see by looking at the diagram that the two lines intersect at the point with position vector minus 1, 5. The question is, could we do this without plotting the graph accurately each time? So because the two vector equations intersect at a particular point, at that point they have the same position vector, so their r is the same value at that particular point. So therefore we can set the right hand sides of the equations equal to each other, and then by taking each of the components separately we can find two equations involving lambda and mu. So from the top row we would get minus 4 plus 1 lambda equals 1 plus 2 mu, and then from the bottom row, the y component, we get 2 plus 1 lambda equals 4 minus mu. We can solve these simultaneous equations. When solving them, the lambda value that we get is 3. Using the lambda value 3 and substituting it back into the equation for R1 would give us minus 4, 2 plus 3 times 1, 1. So multiplying out the second vector and then adding the two vectors together, we get minus 1, 5. That is the position vector that we found when we looked at the two straight lines on the graph. Now you'll notice that we didn't use the value of mu there, we didn't need it. However, when solving the simultaneous equations, we would also have got that mu equaled minus 1. It's always worth checking because you should get the same answer if you use mu equals minus 1 in the second line equation, and that's a good way of making sure that your answer is correct. So if you put minus 1 into the second equation, you also get minus 1, 5 as the answer. So we're now going to look at how two lines in 3 dimensions intersect. So we're going to start in the same way as we did in the two-dimensional case. We're going to put the two equations equal to each other, and we're going to take each component separately to get an equation that links lambda with mu. So we will get from the first line, the x component, 3 plus 4 lambda equals 5 plus 2 mu. For the middle line, we get 2 plus 6 lambda equals 5 plus 3 mu. And then for the bottom line, the z component, we get 1 minus lambda equals minus 4 plus mu. So we're going to need to take 2 of those to start with. So we're going to take the first 2 equations. If we take those 2 equations there, solve them simultaneously, we get lambda equals 2, mu equals 3. Now, in order to check whether the lines do in fact intersect, we need to make sure that those values do work in the third equation. So in the third equation, 1 minus lambda will become 1 minus 2, which is minus 1. And then minus 4 plus mu will become minus 4 plus 3, which is also minus 1. So we've got the same value on both sides, so therefore it satisfies the third component equation. So the two lines do intersect. Now that we've got that, we can take our value for lambda being 2 and put it into the first equation. So if we multiply out this bracket, add the two vectors together, we should get 11, 14, minus 1. Now it's always good practice to then check that the value for mu, 3, also gives us the same point. So although we can say that the point of intersection as coordinates is 11, 14, minus 1, it's a good idea just to make sure that that is in fact the solution. So putting mu equals 3 into the second equation there confirms that 11, 14 minus 1 is the point of intersection. So notice that this is a position vector, but we've actually given our final answer as coordinates. We're now going to try to find the point of intersection of these two lines. So we're beginning the same way, setting the two equations equal and writing down an equation for each of the three components. So we get 0 plus 2 lambda equals 6 minus 2 mu, 5 minus lambda equals 6 plus 3 mu, and 4 minus 2 lambda equals minus 3 plus 1 mu. Again, we take two of the equations. If we take the first two, solve those, we get lambda equals 5, mu equals negative 2. We're now going to check whether those values satisfy the third equation. So the third equation, when we substitute lambda equals 5, mu equals minus 2, gives us negative 6 on the left, negative 5 on the right. Because those two are not equal, we can conclude that the lines must be skew lines, so they don't intersect. In two-dimensional space, if we know that two lines do not intersect, we can conclude they must be parallel. In other words, they stay the same distance apart all the way along and never meet. We know that two lines are parallel if their direction vectors are multiples of each other. So it's quite easy to tell in 2 dimensions if two lines are parallel by looking at the direction vectors and seeing whether one is a scalar multiple of the other. Therefore, in 2-dimensional space, this implication works both ways. If two lines do not intersect, we can conclude they must be parallel, and if two lines are parallel, we can conclude that they will not intersect. If two straight lines are parallel, as in they have the same direction vector, but they also have a point in common, they go through the same point, we can conclude they must be collinear. In other words, they must be the same line. In 3-dimensional space, there are more possibilities. If two straight lines in 3-dimensional space are parallel, then we can conclude that they will not intersect. This is easiest to imagine if we consider a cuboid. If we take two parallel edges on a cuboid, we can see that the lines that pass through these edges are parallel and they will never intersect. However, if two straight lines do not intersect, we can't conclude in 3-dimensional lines that they are parallel. There may be another possibility. For example, if we take this edge on the cuboid, we can see that the two edges are not parallel. However, because one passes along the base of the cuboid and the other passes along the top of the cuboid, we can see that the two lines will never meet. They will reach a point where they're at their closest, but then they will pass each other and not meet. This situation in 3-dimensional space is called skew. So two lines that are not parallel but also do not intersect each other are called skew lines. We're going to prove that these two lines are skew. So the first thing we need to do is check whether the lines are parallel, because if two lines are parallel, they will not be skew. So we're going to look at the two lines' direction vectors and by inspection see whether they are scalar multiples. We can see the direction vectors are not multiples of each other, so we can conclude they're not parallel. We next need to show that the lines don't intersect. We do this by initially assuming that they do intersect and hopefully arriving at a contradiction. So we're going to put the two lines equal to each other. We're going to take the three components and write an equation for each one. So the first component becomes 2 lambda equals 6 minus 2 mu. The second becomes 5 minus lambda equals 6 plus 3 mu. And the last becomes 4 minus 2 lambda equals minus 3 plus mu. In the same way as we have previously, we're going to take two equations to find a value of lambda and mu. We're going to take the first two. We get lambda equals 5, mu equals -2. And we now need to show that if we substitute those values in, we will not get the same answer for both sides. We'll get a contradiction. So here we can see that we do not get the same answer on both sides. 4 minus 2 times 5, that's -6, minus 3 and -2 is -5. So that we can conclude, therefore, that if the two lines are not parallel and they do not intersect, the only possibility left is that the lines must be skew. So we can conclude that that is the case. Now complete exercise 9C on page 207.